What is congestion? What we're going to cover in the next few minutes is exactly what this title suggests. And that might seem like a funny question. Everybody knows what congestion is. But what I really want to convey is that there are two ways of looking at what happens when a road becomes congested. And understanding these two ways of looking at it, they're not mutually exclusive. Both are correct in their own way. But understanding these two perspectives, I think, is going to help us move forward and think about ways to solve congestion and understand why some common solutions don't work, and also understand down the road why some solutions do. So let's get right to it. So the first perspective I want to talk about is, for lack of a better way of putting it, the engineering perspective. Like, what actually happens mechanically when a road breaks down in its level of service and traffic starts to slow down. And so let me start to give you some terms here. There's basically two categories that we sometimes talk about when we talk about congestion. And the first one is called recurring congestion. And that's just what it sounds like. It's the type of congestion that predictably and reliably shows up day in and day out. And so the obvious example of this is sort of peak period commuter travel, right? That, the 405 freeway here in LA at 8 a.m. The second one is called non-recurring congestion. And that's sort of the unexpected or less regular events that create bottlenecks. Perhaps the most common of these is sort of traffic incidents and crashes, whether a road is closed for construction or two vehicles hit each other and slow everything down, street closures for special events, weather-related incidents. These aren't perfectly sort of distinct categories. One of the most obvious ways they interact is that the more recurring congestion you have, the greater the chance that two vehicles will crash into each other. Sometimes you do see someone trying to assign, 40% of the delay in St. Louis is to recurring congestion and 60% to non-recurring. I don't think those are terribly accurate, but it's good to understand these two categories, right? And so just to really drive this point home, here's a classic scene of a rush hour freeway. That's recurring congestion, right? If all these folks are on their way to work or things like that, that's probably going to happen every day. Non-recurring congestion, again, can take different forms. Sometimes it's something really unusual. A road is closed for a parade, and then as a result, all the roads around it are much more congested than they would normally be. That's non-recurring congestion. Another example of non-recurring congestion would be something that's not quite so unpredictable and irregular. For instance, here in Los Angeles, when the Dodgers play a home game, Sunset Boulevard near their stadium gets much more congested than it would be otherwise, right? And so that's also non-recurring congestion. So we have these two categories. Let me give you a couple more key terms for us to work through. So the first one is speed. And I think probably all of us are comfortable with what speed is, but this is basically the distance that a vehicle can cover in a unit of time. So 55 miles per hour. The next one is flow. This is the number of vehicles that pass a reference point per unit of time. And it gets measured as sort of vehicles per hour or vehicles per 5 minutes. This is also sometimes called volume. To give you a sense of how flow can be measured, just imagine standing at a certain point along the side of a road and counting cars as they go by, right? And if 5 vehicles go by per 5 minutes, then that's your measure of flow or volume. The next term is called headway, and the headway is just the time that elapses between vehicles at a certain point. And so it's basically the inverse or the reverse of flow. And then lastly is density, which is the vehicles per unit of roadway. And we measure this often as the vehicles per lane mile of road. And a lane mile is exactly what it sounds like. It's a mile of road in one lane. And we measure roadway capacity in lane miles to account for the fact that some roads are wider than others, right? It's a better measurement than just the total linear distance of roads, which we call centerline miles. Okay, understanding these things helps us then understand a very important point about the way a roadway can function, which is that you can get high or low flow in very different sets of traffic conditions. And let me kind of illustrate that and just kind of illustrate some of these terms. So here you have what looks like a kind of rural highway that is not super heavily trafficked. And so this would be characterized by high speeds, low flow, large headways, and low density. And you can see all that you can't see the speed in the picture, but you can imagine that these cars are moving pretty fast. But you can see the low flow. There aren't too many cars there, right? So if you were to stand along the side of this road, you just wouldn't see too many cars go by you. Part of the reason for that is that there's a lot of space between the cars. That is, in fact, what's letting them go fast, right? And so that's the large headway. And then because there aren't too many cars on the road, the density is low. In contrast, here's a congested urban road, and this is characterized By low speed, right, you can see these cars aren't going very fast. High density, the cars are very close to one another, filling up the road. Low flow, because the cars aren't going very fast, not too many of them are going to go past a particular point in any given amount of time. And then low headways, the cars are very close to one another. There's very little space between them. And I want to emphasize a point here, which is that both of these pictures, right, this one and that one, have low flow, right? Which means that low flow can occur both at very high speeds, when there's lots of space between cars, and very low speeds, right? When cars are very close to each other but not moving. And so if you were to plot speed and flow, the way that it kind of manifests in the typical American roadway, or roadway around the world for that matter, what you would get is what traffic engineers call the backward bending curve, which is what you're looking at right now. This is the plot of speed versus flow. And what you can see is that on the far left side of the graph, that flow is low when speeds are very low, right? Down around in the lower left-hand corner, down around 10 miles an hour or so, but also when speeds are very high, right? Up near 80 miles an hour. And again, just to drive this point home, the reason that happens is that when cars are very close together, they just can't go fast. And when they can't go fast, they can't move past a point very quickly. And then conversely, for cars to be able to go very fast, 80 miles an hour, there simply can't be that many of. So a road that's letting someone travel 80 miles an hour is a road that can't be carrying that many vehicles. So that slide you just looked at was just kind of a stylized depiction. This figure, which I'll come back to in a little bit, is an actual representation of data collected by sensors on the 10 freeway in Los Angeles. And it's not nearly as clean as the sort of stylized picture I just showed you, but it does clearly show that there is a backward bending curve, right? And again, I'm going to describe this more in a few minutes, but what you do see is that flow is quite low when speeds are quite high at 4 a.m., and flow is quite low when speeds are quite low at 9 a.m. Again, I'm going to come back to this. And so what's going on, right? With this in mind, if all that makes sense, we can now start to think about you're driving along close to rush hour in an urban area. What happens when traffic congestion sort of envelops you? And what basically happens is that while you're driving in free flow, if you're not in rush hour, what we say is that a well-functioning road balances high speed and high flow, right? And what we mean by that is that when the road's working the way we want it to, you have a lot of vehicles all moving quickly, maximizing the capacity of the road, that the most vehicles are passing over a given space on the road in a given amount of time as possible. And so when this occurs, what we say is that the density of vehicles on the road is at its optimal point. Now, when traffic arises, all of that starts to fall apart. And it falls apart because the density actually rises above that optimal point. You get a few too many cars on the roadway, right? And so that's what causes delay to begin to accumulate. How does that happen? It's the following. So again, in a stylized, perfectly operating road, drivers are basically going to stay at precisely the minimum safe distance from each other and travel at a constant speed. In other words, if we were all sort of perfect drivers, that when you were driving down the freeway and another car started to drive on from an on-ramp, you would perfectly calculate how far away you needed to be from that car to maintain safety and just adjust your own driving in a way that allowed that to happen and allowed other vehicles to get on the road with minimal friction. Now, of course, in the real world, that's not how driving happens. That basically all of us react to the uncertainty of a new driver on the road in different ways. Some of us are going to, when we see a new car entering the highway from an on-ramp, some of us will speed up to get ahead of it. Some of us will stand on our brakes to sort of really slow down and let that new car in. Some of us will switch lanes, right? And when we switch lanes, the person driving along behind us in that lane, they have to react as well, right? And what will they do? They might switch lanes themselves. They might stand on their brakes. They might try to move into the lane that we were just in. All of this creates a little bit of friction. All of it slows down other cars by just a tiny amount. But because there are a lot of cars, those tiny amounts of delay start to add up, right? That basically, because we all react differently to risk, some of us leaving room between cars, other of us tapping the brakes, and all this uncertainty increases, then collectively all the delay that we're imposing on each other starts to accumulate in what's almost like a shock wave, right? A wave of delay that starts to roll backward down the road. Because as one driver slows, the cars in close proximity behind it are going to slow down as well. And what happens to you when you're sort of driving along and suddenly all the traffic is slowing down is that you're basically driving into one of these waves of delay, right? And then it might ease up for a while, and then you drive into another one, and this is the phenomenon of stop and go traffic, right? So essentially what's happening is that because we all react differently to the uncertainty created by other drivers, we create some friction, and that friction turns into delay, and that delay adds up. And all of that starts because enough vehicles are on the road that it makes us feel like there's some risk to being on the road, right? And so to really think quickly about this, none of this really happens if you're driving at 4 a.m. and there's nobody on the road but you, and then you notice one more car getting on the road, right? You don't feel like you have to react to that other car. But at 8 a.m., when the road is already quite crowded and you see some other car trying to merge onto it, now you feel some risk, and that risk causes that reaction. And that's where you start to get the congestion. Now, just as an aside, occasionally you hear about how self-driving cars could reduce congestion. The logic behind that, and just for the record, this solution, if it ever comes, is probably pretty far off. But the logic behind that is that autonomous vehicles that can talk to each other are going to sort of mathematically compute risk in a much more accurate and consistent way than humans. And so as autonomous vehicles flow onto a road that's already crowded with autonomous vehicles, the idea behind this is that they can all sort of calibrate and communicate perfectly and maintain the correct distances between each other, anticipate each other's reactions, right? And therefore allow more vehicles onto the road with less friction and therefore less delay. Again, I don't tell you that because I think that's going to happen anytime soon. I think we're a long way from sort of like perfectly communicating autonomous vehicles. It's just another way of thinking about what's actually going on when a highway full of cars driven by humans gets into congestion. It's the fact that we all react to risk and we all react differently, right? That creates this sort of friction between vehicles. So the engineering perspective, in short, is this idea that the road hits a density of traffic that kind of tips it into this delay accumulating reaction, right? Okay, so now we come back to this slide that I posted earlier, or this image that I posted on an earlier slide of the I-10 freeway in Los Angeles. And what I want to illustrate with this is something I've hinted at before, but it is an important point, which is that congestion isn't a linear phenomenon. And go back to what I said earlier about the idea of driving on a road at 4 a.m. And a car gets on the road, alongside you. Probably that car will get on the road and you'll be on the road and neither of you will have to slow down, right? There's plenty of room. And then another car could get on the road and none of the three cars would have to slow down, right? But at a certain point, another car is going to get on the road and then all of you are going to have to slow down a little bit, right? And so that's what I mean by nonlinearity, which is that up to a certain point, a road can absorb new cars with no delay at all. Once it hits that point, delay really starts to accumulate. And you see this very clearly in these data from the I-10, which is that at 4 a.m. when the I-10 is pretty empty, what you see is a sort of low flow and high speed, that the average speed is about 68 miles an hour. You're moving about 133 vehicles per 5 minutes. And it stays that way if you follow the graph from left to right for quite some time. And you can just imagine that this is still the early hours of the morning and more vehicles are getting on the road, but not enough to slow it down until if you look over to the right at 5:35 a.m., you see that the flow is quite large, right? It's a 607 vehicles per hour. And the speed has declined by not by a tremendous amount. You still kind of have the vehicles moving in free flow. They're going about 47 miles an hour. But then after that, the flow and the density hit a point where everything starts to fall apart. And you can see the line you see that backward bending curve come back until at 9 a.m., sort of the height of Los Angeles rush hour, both the speed and flow have fallen, that you're moving 493 vehicles per 5 minutes and only going 35 miles per hour, right? That after those 550 or so vehicles, each additional vehicle has large negative effects on speed. And I think this is something that's sometimes hard to grasp, right? Which is that what that means, among other things, is that a really congested road is actually, despite the fact that it looks very crowded, is actually moving fewer vehicles, right? And this is an image of the SR91 expressway in Orange County. And what you see, and I'll come back to this in part 2, what you see right in front of you is the tolled part of that expressway, where you have to pay to get on the road. And on the right, you see free lanes, right? And so there's 2 tolled lanes and 4 free lanes. And just in a cross-sectional sort of the static image that we see, this is just a snapshot, it really looks like there's many more cars going by on those 4 lanes than on those 2 lanes. But if you measure the flow of the 2 lanes and the 4 lanes, what you actually see is that they're almost equal. And the reason for that is that on the lanes on the left, the cars are moving so much faster. If you took this picture 5 minutes later, many cars would have passed by in the lanes that are right in the foreground, the 2 lanes that are tolled, while many of the same cars would be in the image on the right, right? The fact of that high density, the fact of that low speed means the flow is low. So, and this is sometimes hard to intuit in many ways, but if you've ever watched the old TV show, The Three Stooges, there was a famous gag in The Three Stooges called the doorway gag, which is that the Three Stooges would all get excited about something and they try to run through a door all at once, and as a result, they get stuck, right? And what basically happens in traffic congestion is very similar to what happens in the doorway gag, right? Which is that precisely because so many people want to get on the road at once, they all slow each other down and they can't move through as quickly. And what happens in the Three Stooges is that the Mo, who's the leader of the Stooges, tells everyone to spread out. And then when they spread out, they can all walk through the doorway very easily and get through. And this is, if you think about the Three Stooges as a mini traffic problem, right, you can start to see how this happens, which is to say that if you took a snapshot of the Three Stooges while they were in the doorway, you would say that the volume was pretty high. There's 3 people in the door, but the flow is pretty low because they're stuck, right? Whereas if you let them each walk through individually, you would say at any given moment, the number of people was low, only 1 person in the door, but the flow was high because they're proceeding through very quickly. The same thing happens on the roadway, right? And it's another way of just emphasizing this is not a linear phenomenon. Okay, so that's the engineering perspective. That's how I think a civil engineer might look at the problem of traffic congestion. What we're going to do in the next chapter is look at the economic perspective, and I hope you'll join me for that.